All right, welcome back, everybody. This will be the last part of section 3.6. We just want to do a couple more examples to illustrate some of the ideas from this section. In these first two examples, we're going to be factoring polynomials. So the directions say factor the polynomial completely and find all its zeros. State the multiplicity of each zero. So I figured we would start with number 29 here. So this one will be x cubed plus x squared plus 9x plus 9. So this one is degree 3. We're going to expect 3 zeros and 3 linear factors. Looking at this one, it looks like this one actually is going to factor by grouping. So we're going to go ahead and do that. I would always look and see if a polynomial you're given is going to factor even a common factor or factor by grouping or something before getting into some of the bigger tools that we have, like Descartes' rule of signs and so forth. So rational zeros theorem. So factoring first, I can see that the first two terms have x squared as a factor, which will leave behind x plus 1. And then the second two terms have 9 as a factor, which will leave behind, again, x plus 1. Okay, so then we have a polynomial that consists of two terms, each of which has x plus 1 as a factor. So we're going to factor out that x plus 1, and we'll be left behind with x squared plus 9. All right, so now x squared plus 9 doesn't factor using real numbers, but we can look at it as x squared minus -9, right? X squared minus -9 is the same as x squared plus 9. So you can just kind of look at this thing as a difference of squares, right? So the difference of squares formula says a squared minus b squared is a plus b, a minus b, okay? So we're going to use that to help us factor this thing. So let's do that. So we will have, let's go down one more actually. We'll go x plus 1. And then our x squared minus 9 will factor as x plus 3i, x minus 3i. The 3, of course, is the square root of 9. And then the fact that this was a plus 9, when we wrote that as x squared minus -9, we're taking square roots of -9. The two square roots of -9 are 3i and -3i. All right, so directions. What do the directions say? Factor the polynomial completely. Okay, we did that. And then find all its zeros. So the zeros are -1 and -3i and 3i. Okay, and then it said to state each multiplicity. So multiplicity is 1 on each. Okay, so all of the zeros had multiplicity 1. All right, so what else have we got? We did 29. Let's see number 34. So 34, it says p of x is equal to x to the 5th power plus 7x cubed. So once again, I'm going to take a look and see about any common factors for that one first. This thing is only 2 terms, which is great, but it's degree 5. So we're going to end up with 5 zeros. So pulling out the x cubed, we'll have x cubed, x squared plus 7. Okay, x squared plus 7, we're going to kind of look at this as x squared minus -7. And then we can factor it as a difference of squares. So if you're thinking, okay, well, 7's not a perfect square, that's true. But its square roots are going to be square root 7 and minus square root 7. So writing that as a product of linear factors, we'll have x plus square root 7 times I and x minus square root 7 times I. Okay, again, once again, you can always double check that by multiplying that out to ensure that you get what you expect. So there's our factorization. So that's pretty great. That wasn't too bad. As far as writing down the zeros, we had -7i, we had 7i, and 0. The first two have multiplicity 1. And then that 0, the x cubed as a factor, gave us basically 0, 0, and 0, right? So that has multiplicity 3, okay, for that last one. All right. Okay, so on to our last set of examples for this. So in this one, we're factoring. It says a polynomial p is given. We're going to find all the zeros of p, real and complex, and then factor completely. So we'll be doing that once again. So here, we'll do number 11. It says p of x is x to the fourth power plus 2x squared plus 1. So on this one, once again, I can see by the structure of this that if I make a little substitution, then this thing is going to look actually like a regular quadratic function that I'll be able to factor. So we're going to make a little substitution. I'm going to let a equal x squared. What's a? It's x squared because I just said so. Okay, so we're just defining a new variable. I'm going to call it x squared. If a is x squared, then x to the fourth power will be a squared. Okay, so then our original function now, x to the fourth power is a squared. Our x squared is a, so this will be a squared plus 2a plus 1. And that's easier to factor, right? So this thing will factor as a plus 1, a plus 1. Okay, now if you like, you can undo the substitution. Our a was x squared, so we'll have x squared plus 1 times x squared plus 1. And then these will factor as a difference of squares again. This will be x plus I, x minus I, x plus I, x minus I. Okay, so now our zeros are minus I and plus I, and both have multiplicity 2. Okay. So there were 4 total zeros, which makes sense because this polynomial was degree 4. It had I as a 0 occurring twice, and minus I as a 0 also occurring twice. All right, so our last example is going to be number 16 here. We're going to take x cubed minus 8. That will be our p of x. Okay, and so what we want to do is, again, factor this thing and then find its zeros. It's kind of neat because if we're finding its zeros, x cubed minus 8 equals 0 means that x cubed equals 8. So we're going to find the 3 cube roots of 8. As it turns out. Of course, you know probably already that one of the cube roots of 8 is 2, and so that's going to furnish us with one of our zeros. So we can tell by looking that 2 is a 0. Okay, p of 2 equals 0. Okay, since you kind of figured out already what one of the zeros is, then we'll use division to see what else there is, right? This thing is a difference of cubes. You may or may not remember the difference of cubes formula from algebra. If you don't, that's okay. We don't actually need it right here. So we're going to divide 2. It was 1x cubed, no x squareds, no x's, minus 8. Okay, so we're going to divide. All right, so now multiply and add. 2 times 1 is 2, and then 0 plus 2 is 2. 2 times 2 is 4. 0 plus 4 is 4. And then 2 times 4 is 8. Negative 8 plus 8, it better be 0, right? And since 2 was 0, so that's it. So our p of x is looking now like x minus 2, x squared plus 2x plus 4. All right, and that part is not a perfect square. It's not even factorable. So to find the remaining zeros, we're going to use, this time we'll go ahead and use the quadratic formula to get this done. So we're just going to be looking at x squared plus 2x plus 4. We'll set that equal to 0. So quadratic formula, x will be minus 2 plus or minus square root of 4 minus 4 times 1 times 4. That's all over 2. Simplify that radical. So negative 2 plus or minus square root. Down here under the radical, we have 4 minus 16. That's negative 12. That's all over 2. And then that square root of negative 12, let's put this all on hold and figure out that square root of negative 12. That's going to be 4 times negative 1 times 3. Square root of 4 is 2. The square root of negative 1 is an I. And then the square root of 3. Can't do anything with that. So we'll have that as 2 square roots of 3 times I. That will be that radical that we have in the numerator. Okay? So we'll have 2 plus or minus 2 square roots of 3 times I. That will be all over 2. We're going to separate this into 2 separate fractions now. So we have 2 over 2 plus or minus 2 root 3 over 2 I. Okay, each of these, we're almost done. Each of these fractions simplifies. 2 over 2 is just 1. And then 2 root 3 over 2 is going to be root 3. And so we'll have 1 plus root 3 I, 1 plus or minus. Okay, so let me double check that, make sure that, because I think I lost a 2 in here someplace. Let me find that. All right, so it turns out that was fine. I thought I had messed something up there, but but it turns out that it's all right. So our other zeros end up being 1 plus or minus root 3i. So our zeros in all are 2 and then 1 minus square root 3i. And then 1 plus square root 3i. All right, and those are the 3 cube roots of 8. So it can seem kind of funny at first, but if you like, if you're interested, take that one of these other ones like 1 plus root 3i. If you feel like practicing your complex number multiplication, multiply that out and make sure that you get 8. All right, so that does take us to the end finally of section 3.6. Let me know if you have any questions on it, and have a great day.